Good morning, class. So today I'll be actually going for the extra problems which I didn't had time to discuss, but let me just do that here. So the first problem is, and we will be actually addressing the normal force here. Normal force and the contact force. This is the best example that you can get. Okay, now let's go for it. So in this, you have three identical 0.7 kilograms blocks of ice and are lined up on a horizontal frictionless surface. The leftmost block is pushed with a force 18 Newton to the right. So what is the magnitude of the force between the block 2 and 3? So basically the question is, you need to find out the contact force between the 2 and 3. Okay, now let's try to understand how to go for it. Now the first thing is, again, as I said, the steps are to write down all the forces which are there, which you don't see in the present diagram. So let's try to see how you can draw all the forces. Okay, so first of all, let me just enlarge it. Okay, first of all, the obvious are the normal forces. So the normal forces are this, for the first one, n1 vector, and the weight for the first block. Okay, second is again the normal force n2, and then you have the weight, and finally this one, and then the weight. Simple enough. Now since I have mentioned that all of those are identical, so we will basically, the notations are just for completeness, but we will be using the same masses. Now the contact forces which we did last time, they will be equal and opposite from the contact of the adjacent masses. So for example, between 1 and 2, we already have understood that the contact force on 1 due to 2 is this. So the contact force on 1 due to 2, and then the contact force on 2 due to 1. Understood? Similarly, between the 2 and 3, we will go for the contact force on 2 due to 3 and 3 due to 2. Okay, let me just make it a bit more, bit more clear so that you can see all the indices very clearly. I hope this is clear enough. Okay, now since we have done each and every force, so there are no other forces that needs to be drawn. Okay, now let's go for the object 1 and do all the steps that I did. Okay, so for the object 1, first things, you have drawn the forces. The second step is, for the object 1, you do the free body diagram. Now for the free body diagram, you just focus on the object 1. So write down all the forces that is there for the object 1. If you have just noticed right now what I have done, I have basically this force, I just put it like this. There's no harm, because you need to understand that applying the force on this side or just making it on the other side doesn't change anything. It's just for the convenience that all the force originate, all the vector tails should be originating from the dot and then the direction in which it has been applied. So even if the force is applied from the left to right like this, you can easily put it like this because ultimately the force is towards the right. Okay, the direction is not changing. Understood? Now, since we understood here, even from the contact force, you see that I have only collected that force for the block 1, which has the indices. The first indices is signifying on which the force is applied. So for example, when I'm taking the contact force, keep in mind the first index, sorry, so for the contact force, the first index on which the force is applied, let's say the index is A, the B who is applying the force. Okay, understood? This is basically for all the contact force. Is this point understood? Now, going forward, since we understood and we wrote all the forces, the next step is to write it in terms of the coordinate space system. Now, again, since it's a flat, we will be going for a flat coordinate space. So try to understand that if you have noticed yet, my coordinate space are always and always according to the surface. If the surface is flat, you will see the coordinate space is also flat. If the surface itself is inclined, the coordinate space will also be inclined, and we will be discussing that after this. Okay, now since we understood the coordinate space, let's write down all the forces. Okay, so the force F is F hat. My F hat is X hat plus 0 Y hat. My F12 is F12 hat. Now F12 hat is negative X hat plus 0 Y hat. And then finally you have the normal force, which is given as like this: 0 X hat plus 1 Y hat, and then the weight, which is zero X hat negative Y hat. Okay, so there's one more subtle thing that you need to understand. So let me just write down all the forces here. We understand from the Newton's third law, that the magnitude of the contact forces are same. Okay, the magnitude of the contact force will be same. Okay, so we'll be using this fact. Not only that, the direction, as we noted, the direction is is basically bang opposite to each other. So if you have decided the direction of one, the other one will be on the exactly opposite side. Okay, good. Now since we understood all the forces, now I can write all those forces, I can consolidate everything. So let's see, let's write all of them very neatly. Okay, doing some notational mistake, but for you, please be careful. Okay, so you have this, and then you have the final one. Good. Now, when we add all of them, so what do we get? We have, let's say I'll copy it here, since I don't have space. So all the net forces basically is just adding of all the vectors, comes out to be F minus F12 x hat plus N1 minus W1 y hat. And if I have not yet mentioned, the acceleration of the entire object is on the right hand side or on the plus x direction. So for this also, the acceleration comes out to be here. Okay, so basically a vector is a x hat plus 0 y hat. Please notify that your acceleration, if it is not mentioned, you take a generic direction, or every component is just generic ax and ay. But if you know it, just write it for each object. Okay, now once we know the net force, this is equal to, so F1 net this is equal to ma, Newton's second law. So Newton's second law, we just applied it on the last step. Now the final step is collecting the x and the y. Okay, F minus F12 ma and N1 minus W1 is equal to 0. So we got our first equation. Fine. We do the same steps for the next one. Okay, let's do the next one again. Okay, now for the next one, let's understand what all forces are there. So we have the normal, we have, pick out all the forces in the contact, which is first index 2. We have this, and then we have W. Fine, good. So let's go back and draw the free body diagram. Now the full free body diagram, we have the into, then we have F21, then we have the F23, and finally we have the W2. Okay, since we drew everything again, notice that what I've done here, I have, since the direction is the same, I just shifted these two in the sense that the tail is pointing from the object and then directing towards the direction it is going. Understood? That's basically how you do the free body diagram. Now, writing all the forces, the same drill, there's nothing different, the same drill. So you have N2 equal to 0 x hat plus N2 y hat. Then you have W2 x hat minus W2 y hat. Then you have F23, which is negative F23 x hat plus 0 y hat, and then F21 x hat plus 0 y hat. Now, since we all did this, I'll give you 1 second to add all of them. Okay, it has written everything. So let's write all of them. Good. So you have the net X force plus, all right. Now again, for this one, we also know that the acceleration is left to right. Now, the whole point here is why I'm taking the same acceleration is just by the intuition. So you have the 3 blocks of ice. So when you're applying a force on them, each one of them will be accelerating with the same speed. It's not that this one will try to go forward faster than this one and then this one. Everyone will move in unison with the same rate. Okay, that's why. So, having said that, so applying the Newton's second law again, we get the same equation. What we do, now we open it up, and I'll just skip a step, but it's not for you. You will do the steps. You capture the x component, equate it with the x component of the acceleration. So for example, this is equal to m, okay, and then y hat is again this. So we got the second equation also. All right. Now for the third one, again, let's go back and see what the third one is. Now for the third one, the first index is only one force. Then you have the N3 and W3. Fine. Now let's draw out that. Okay. Again, the same drill, writing out all the forces. F32 is F32, F32 hat, which is F32 hat is X direction. Fine. So let me write down all of them real fast so that we don't waste any time. Okay, since we wrote all of them, there's nothing left. We just write the entire force in entirety. Okay, now the net force for the third one is given as right, and then you have this N3 minus W3. This again, same acceleration that we all did. Again, the same thing that you get. So F32 is MA and X hat is N3 minus W3, 0. This is the third equation we got. Okay, now let's try to consolidate all this first, second, and third equation. Okay, so the first equation we got is this. Let's collect it. Okay, then we have the second equation, this. What the hell? Okay, let's repeat it. Keep notice that for the object 1, the first index is there. For the object 2, the first index is 2. Now for the object 3 is 3. Now also keep in mind, we have kept in mind that the magnitude of the contact forces are same. So since they are same, I have free to use any of the indexes. Okay, so for my convenience, I will just take the first index. So what I'll do, I'll actually change whichever is in the second index with the one with the first index. Okay, for example, this entire equation can be rewritten in terms of the new thing that I did. 1, 2 minus F23 equal to MA F23. Understood? I just changed the 2, 1 to 1, 2 and 3, 2 to 2, 3. Just kept one of them. That's totally fine because they're equal. So I'm free to choose one of them. Now, here comes the entire thing. So we need to find out what this is. In the sense, the contact force between 2 and 3. Okay, this one. Right? Either this one doesn't matter because the magnitude is same. Now, in order to do that, we need to find out. We already know the acceleration. We already know the mass. We don't know the acceleration. Now, the fastest way to do that is there's a mathematical technique. What we basically use is when we know that all the forces, if you see, they are kind of canceling out in the sense. Okay, so if we add them up, if I add the equations, what do I get? I actually get the F minus F12, that's the first equation, plus F12 minus F23. This is the second equation, plus the third equation on the left hand side, and on the right hand side, the first of the right hand side, the second of the right hand side, and the third on the right hand side. Good. Now, if you see beautifully, if you open up the brackets, or in your case, parentheses, you can actually see everything cancels out beautifully. Right? Now the force basically comes out to be this, and the acceleration is this. Wait, let me just write down. stepwise, not to skip step. Fine. And just we put it back on this equation to get the F23. And then what do we get? F23 is m times F upon 3m, 1/3 of the force. Understood? Now pay close attention what is happening here. This is basically kind of a sanity check actually. Why? Because if you see here, if I assume that entire of this is just one block of mass 3m, the Newton's second law is very simple. It actually comes out to be this. And this is exactly what we are getting. All right? Awesome. Good. Now, let's do the next one. Now, for the next one, we are doing an inclined plane. As I said, this is a very special case, and you need to understand how I'm approaching it very carefully. Okay? Because this is the first case that we are discussing where the coordinate space itself will be inclined. Okay? So let's do this. Okay? So the box is basically of mass m. Okay? And here, the coordinate space that we are taking, that will be along the surface. As I said, my coordinate space are always and always along the surface. Okay? Good. Now, when you're taking along the surface, it will be a bit of the, you may say I'll be testing, or you will be tested on your geometry here as to understand the angles between each other. Okay. Now let's try to understand in this topsy-turvy coordinate system, what is my quadrant now? Again, this side will be the first quadrant, this side will be the second quadrant, this side will be the third quadrant, and this side will be the fourth quadrant. Okay, it's nothing but the same thing, I just tilted it. Nothing has changed. Now, having said that, let's draw out all the forces. Now, for the force, again, you have the weight. Now, again, the weight is always and always directed downwards. Okay, the weight is bang downwards. However, the normal force will be from the surface, the thing that you get from the surface towards you. Okay, simple. Since we understood this, we can actually now write down the entire um, Newton's, basically the free body diagram from here. So let's try to do that. First of all, before doing that, let's try to understand how this weight is making an angle with the new coordinate system that we have taken. For that, let's try to understand the geometry here. We understand that this line is basically parallel to this line because this is straight and the weight is applied straight downwards, right? Okay. Now, this is a right angle triangle. That means this angle comes out to be 90 minus theta. Fine. Now, if this angle is 90 minus theta, so if this is parallel lines, this will also be 90 minus theta, right? Same side of the parallel lines have the same angles. Okay. So this becomes the same. Let me just, before doing that, let me just put a symbol so that we don't get lost. Okay, now focusing on, now here let me just write down somewhere alpha is 90 minus theta. Okay, now coming back here, this is a coordinate space, which basically means it's an orthonormal basis. In other words, the directions are again same 90 degrees to each other. If they are, then if this is 90 minus theta, then this becomes theta. Okay, so hence we understood the weight is making an angle theta with the y-axis. Pay attention. It's making an angle theta with the y-axis. Okay, so what we have learned, if it is in the third quadrant, that means it is negative, positive, and if it is making an angle with respect to y, with respect to y direction, then the w dash, or the direction of the weight, comes out to be negative sine theta x plus cos theta y. Cos theta is y because it's actually making an angle with the y direction. Okay, it's not sine theta x and cos theta y, it's flipped. The reason of flipping is because the vector is making the angle with the y direction, not the x. Okay, so this was the only point where you'll be getting a bit confused. So please ask me if you're getting confused in this. Now, the normal case is very simple. X hat and then y hat. So the net sum of the forces comes out to be negative w sine theta x hat plus w cos theta. Oh, sorry, it's in the third quadrant. I made a boo-boo. So in the third quadrant, both are negative. So sorry, guys. So they both are negative. Okay. And hence, n good, right? Now, since we don't know in which direction on the plane the acceleration is going, so we just presume it. Now, basically, we know in which direction it's actually this direction. It's basically slide down. So we take the acceleration to be negative ax hat plus 0 y hat. Why negative x hat? Take a notice, my x-axis is tilted itself, so it will be along the x-axis. Okay, so putting everything together, we get w sine theta cos theta a set. Finally, we have w sine theta ma and n minus w cos theta is 0. Basically gives me the acceleration to be g sine theta and the normal to be w cos theta. Okay, so the main thing that the takeaway from the inclined plane is your coordinate space itself gets tilted. You need to bit work on your geometry as to understand the angles of the forces with respect to the new coordinate system, so which I've laid out here, and then do the rest of the forces. And the steps remains the same. The step doesn't change. The steps remains the same. The moment you understand how you're doing the angles, the steps remains the same. There's no difference in the steps. Okay. All right. Awesome. So this was all about the supplementary problems. Okay. All the best, guys.